This video will look at the locations where the derivative of a function equals 0, which are called function critical points. So we have some general function of x, f of x, has some graph versus x of who knows what it looks like, unspecified for the moment. So f of x, as we mentioned, is the value at x. F prime of x, d dx, is the slope at x, instantaneous slope at that particular location. And f double prime, d squared dx squared, the second derivative, is the curvature at that point at x, or the first hint about what the curvature is. All right, so we want to know a lot of information about the points at which the f prime of x, at which the first derivative of x equals 0. These are points at which there is no slope for the function, and these are points which are referred to as critical points. So at a given critical point, all four of these points that I have marked on this graph here are supposed to be points where the slope of the function is equal to 0. So where the first derivative with respect to x is equal to 0 is a critical point. And to classify what kind of critical point it is, you look at the second derivative. So the second derivative of f with respect to x, if it is positive, then the curvature is sloped upwards. The derivative is increasing. So that means you're at what is called a local minimum. So your slope is at 0 and you're increasing, and you were decreasing before you got there. So that means you're at what's called a local minimum. You're at the lowest point in the kind of region immediately around that point. If the second derivative is below 0, then it is what's called concave downward. It is curving downward. The slope was positive, now it's 0, and it's going to be negative at the next point. So that is a local maximum in your function. That's the highest you'll get in the immediate neighborhood around that point. And if the second derivative is equal to 0, then we can't say. We have to look at some higher derivatives to figure it out. It might be a minimum, it might be a maximum, it might be a saddle point, or a point where you go up reaching it and then you go up coming out of it as well, or maybe down. But if we don't have the second derivative, which is non-zero, then we don't have a clear indication until we look at some higher derivatives or just graph the function. All right, so each of those I mentioned was a local minimum or a local maximum. These two are both local minima. But there's only one point which is the smallest possible value of f of x over a specified range. So that smallest value is called the global minimum. So if we assume that this function keeps going up to the left here and it keeps going up to the right here, then this particular function is the global minimum. Both of these are local minimum, but this one is lower than that one, so this is our global minimum. And similarly, the highest value we have over the entire range of the function would be the global maximum. If we imagine that this function reaches a maximum here and then goes down, and then we imagine this function goes down over here as well, then this whatever point where this flip occurs here would be the global maximum, the highest point on the function overall. So this is a local maximum, but it is not a global maximum because other points are higher than it. Okay, so the critical points are what help us find the candidates. They find us what are local minima and local maxima, and they find the candidates for all of our global maxima and global minima. So the candidates for global maxima and global minima are the critical points and then the lowest and largest values of x over our specified range. If it's the entire domain of the function, then this might be minus infinity and plus infinity, but just whatever function range that you're interested in. Okay, so let's do an example. So we have f of v, function of v equals av squared e to the minus kv squared. And we're interested in this over the range of 0 is less than or equal to v is less than or equal to infinity. All right, so what's the global minimum and global maximum over this entire range here? All right, so we'll take the derivative. We'll take df of v dv is equal to, so this is going to need some product rule and chain rule. You can check yourself from my result. I'm going to have av e to the minus kv squared minus 2kv cubed e to the minus kv squared. And we're interested in the critical points, which are locations where that is equal to 0. So now we're solving that this polynomial, or this function, is equal to 0. All right, so when is this function going to equal 0? So we can factor some things out. We'll factor out, actually we have an a over here as well. Okay, so we're going to factor out some things. So we're going to have av e to the minus kv squared is factored out from both terms, times, and then we have 1 minus 2kv squared equals 0. So just factoring out av e to the minus kv squared from both terms. All right, we solve where this equals 0. Any possibility where it equals 0 is a legitimate answer. So v, there's a v out here, so if this is 0, everything's 0, so v equals 0. This e to the minus kv squared is going to equal 0 at v equals infinity. E to the minus infinity squared is e to the minus infinity, which is 1 over e to the infinity, which is 0. So infinity as well, but the point in the middle, if we solve this middle term here, is going to be the square root of 1 over 2k. So there are 3 critical points over this range for this function: 0, square root of 1 over 2k, and infinity. All right, so we could evaluate what the second derivative is for each of these to know what kind of critical point they are, but I'm not going to do that. Number 1, because the second derivative is going to be complicated, and number 2, because I'm lazy. So I actually just know, based off of experience with this function, that this is a minimum, this is a minimum, and this is a maximum. But what we can do now is evaluate the function at these given points and see what the values are. So f of 0, if v equals 0, this is 0, this whole thing is 0, so that's 0. F of the square root of 1 over 2k is going to equal, well, square root of 1 over 2k squared is 1 over 2k, so this part in front is a over 2k. And then we have e to the minus kv squared. 1 over 2k times minus k is going to be e to the minus k over 2k is going to be e to the minus 1/2. So that'll be e to the minus 1/2, which is some number that'll be around 1 point something. And then f of infinity, if I put an infinity in this exponential, I get 0, so this is going to be 0. All right, so we have a minimum here, a minimum there, and a maximum there. You can convince yourself that the second derivative is positive here, positive there, and negative there. So in this case, what we have ended up with is these 2 points are both the same. And note they're also the minimum and maximum values of the function. So if these weren't critical points, I would have to include these as well to evaluate. So these are the global minima because they're each the same value, so each of them is the global minimum. And then this value here with the highest value critical point and a negative second derivative is going to be the global maximum.